Okay. So this work is based on an interesting decomposition of the Yang-Mills gauge field, which was developed by a few people, okay, including Professor Y.M. Chow and Duan Yishi and Ge Mulin many years ago, and then Fajeev and Niami. And also was further developed by Shabanov and Kendall. And Professor Y.M. Chow and Kendall was invited, but they didn't make it. So I was hoping they can give some introduction to their decomposition, but anyway, we'll see how much you can get there. Okay. I'm going to use this decomposition and this new set of variables to formulate the QCD string, or so-called flux tube. Based on an anomaly inflow scenario, if you're familiar with anomaly inflow, it's called the Garland-Harvey anomaly inflow scenario. And I'm going to show you how to produce a topological charge and topological current term. And then we use this formulation to address the U1 problem and also strong CB problem. And if time permits, we can talk about a little bit of other applications about the chiral magnetic field and also Josephson effect, and etc. The other, I'm going to focus on the QCD part, but the other extensions, like in cosmic string or in electroweak strings. I want to bring your attention to Professor Christian Huang's, and his student Tip Ten's work about more than 30 years ago. And he predicted something called vorticon in the electroweak vacuum. And it's supposed to be discovered at 3 TeV. Okay. But anyway, I'm not going to talk about this. I want to focus on QCD. So QCD flux tube is a very interesting configuration. If you know, of course, there's another configuration called the instant configuration. And the instant configuration can be used to solve the problem of U1, the mass of the eta mesons. And also the introduction of the theta world scenario. Okay. But that causes like another problem, which is the strong CB problem, because from the neutron electrodynamic moment experiment, the value of theta is very small, and you cannot imagine in a theory which is about the strongest force in the nature, you have such a small parameter. Okay? And then here comes the beautiful mechanism by Patrick Quinn, and then also they introduce a new particle called the Xiong. Okay? This is the Xiong story. And the original Xiong model is ruled out many years ago, but there's some extensions and variations. And they're still waiting for the both high energy experimental and also cosmological tests. But here I'm going to show you a different approach to these, to address all these two problems. And it's based on flux tube model. And the big picture is, I'm going to use this, I call it Chow, Fajeev, Niami decomposition. We use this decomposition and the new variables to build the QCD flux tubes. Okay. And then we're going to derive some effective, I call the gauge nonlocal Nambu-Jona-Lasinio effect ratio. I'm going to use that to study the states. And then I'm going to show you the localization of Quark zero modes in the flux tube. And you will see because that's a two-dimensional topological defect, then you see the appearance of the gauge anomaly. And the gauge anomaly has to be canceled by through this anomaly inflow mechanism. So something has to happen in the bulk. Okay. And it turns out to be a topological current term, which is a coupling between the, so I call it supercurrent coupled to Chern-Simons current. K mu is a Chern-Simons current. Alpha is some phase. I'm going to show you what it is. And please note that this is a derivative coupling. Okay, that will be used for in the strong CB problem. And you can find more details in my two papers. I'm going to start with the this vorticity in the Higgs-like vacuum. Okay, this includes like the superfluid heading for in a rotating bucket, and you can see if you do that, you can see the formation of the quantum vortices. And this is a vortex lattice. And actually, the figures I copied from Wikipedia. You can check those figures by yourself. And you can see actually the number. I mean, once the angular velocity goes beyond some critical value, and then you see the appearance of the vortex lattice. And the number of vortex lattice is proportional to the angular velocity. Okay. And similar phenomenon happened in the type 2 superconductor called the Abracos vortex lattice. Okay. The rotation is replaced by the magnetic field. So, but the mathematical formulation basically the same. Okay. And also, actually, I also heard from the first talk of this afternoon about the BEC, I mean, the vorticity vortices in the BEC, okay, both ions and condensates. So you also see the similar phenomenon. All this can be described as this nonlinear Schrodinger equation, or some people use the Gross-Pitarevsky energy functional to start it. If we generate to the relative test cases, of course, it will be the nonlinear time Gordon, okay, because for the Lorentz invariance. So actually, we write this very simple. I mean, this is like this is what called the Higgs-like. It's a U1 model. It's a U1 Higgs with this Higgs-like potential, and then we introduce some interactions to induce the vorticity. Okay, so you need something to put in the vorticity. So actually, this term is in the form of a current-current interaction. Okay, the one current is proportional to the derivative of the phase of the complex field. Then I want to remind you the similarity between this current interaction and the previous term I mentioned. Okay, the coupling between the Chern-Simons current and this phase. So it looks like quite similar, but then the question would be how to identify the phase in QCD, and also how to identify this complex field in QCD. So I'm going to show you this numerical simulation calculation we have done recently, last year. So we just use the nonlinear Klein-Gordon equation, and then we use the current interaction to produce the vorticity. And then you see this three-dimensional vortex lattice. Okay, so this picture shows how complicated the phase structure of this Higgs vacuum would be. Okay, because later on I'm going to show the complex field phi actually can be identified as the Quark condensate. So you may wonder, so I can just rotate the phase away by rotating the phase of each quark, but because of this topological obstacle, you cannot do that. Okay, so that's the main point of this work. So this is a identification of the complex scanner. So I use this to use the Quark condensate, which is the order parameter for chiral Brooklyn, to work as the complex scanner. Okay. And alpha is the phase of the complex field. Here I'm going to skip some basic stuff about the QCD strings or QCD flux tube. This version it's not new. I mean, this was started many years ago by a lot of people. Okay. So I'm going to skip all this. I'm going to also skip the details of this beautiful composition. Okay, but you can check in the original paper or a very nice review I found recently by Professor Kendo, okay, Japanese group. So you have this composition, and then we keep going, and then as I said before, we're going to reach this effective action. I call it the gauge NJL, the Nambu-Jona-Lasinio effective action. This is the gauged piece, okay? This is the gauged piece. If you remove the piece, then it will be the original NGL model, okay? But because of this term, we can use this effective action to describe the flux tube. And actually, you can use all the NGL technology to compute the gap equation and also the effect to compute the effective potential. Okay, there's going to be something like this, like a Higgs potential. Okay? But you have the new ingredients, which is the gauge field. The abelianized Yang-Mills gauge field. So these two people, Suganuma and Tatumi, has considered similar situation before. Okay, they consider, but their motivation is to say, under water condition, the chiral symmetry can be restored, given strong counter-magnetic field in the flux tube. So their result is this is the theoretical value for the chiral symmetry restoration, and this is the value they used from the usual meson phenomenology studies. So their conclusion is it's possible that inside the flux tube, the chiral condensate vanishes and the chiral symmetry is restored. So we have a space-dependent Quark condensate. Okay, so that's actually the amplitude of the order parameter I described before. Okay? So I just showed that the Quark condensate has the right boundary condition needed for a vortex configuration. Okay, because the vanish is zero inside and almost the constant outside. So that's the ideal boundary condition for vortex configuration. So we seek solutions. We're looking for solutions of with vortex configuration for this Quark abelianized gauge potential and the Quark condensate or mean field system. Okay, this psi A phi system, and this system actually this kind of system has been intensively studied by a few groups. You can see there's even some index theorem built by Erika Weinberger to study the number of vortices, something like that. Okay. So we assume, we didn't do the numerical solution to prove such vortex configuration exists, but we assume the vortex configuration is energetically favored. Okay, so this means that's the ground state. And we treat it as background. So then we couple it to fermion, to the quarks, and then it becomes a fermion vortex system. So then we solve it. And the interesting thing is the quark zero mode. Okay, the quark zero mode has an interesting exponential decay profile, which means the quark zero mode is localized in the flux tube. Okay, and because these quarks are coupled to the abelianized gauge field, so then if you compute it, you find that there's a gauge anomaly appears in this string-like topological effect. So how to cancel out? Because in the original QCD there's no gauge anomaly. Okay, there should be gauge anomaly free. And actually, Carl and Harvey solved this problem by realizing that the massive mode of the Dirac, the quarks, leaving off the vortex, is going to be contribute, and actually you can compute the induced current by the massive mode, and actually just call the result. And then you can convert this induced current to a bulk effect fraction, a bulk term, which looks like so that's the ideal term, the term I mentioned. Okay. Of course, you don't have to stick with the abelianized story. The non-abelian case actually works as well. So this is the picture of this I call it's like a charging anomaly battery. So this is the quark on the quark, and the flux tube. I mean, the field lines were squeezed into a flux tube. So inside the chiral condensate vanishes, outside is constant. And then the induced current, I mean, you can take any cross-section of this tube, and then you can see the inflow of the induced current from the outside vacuum. Okay? And that's configuration also very similar to the Hall effect. Okay, so basically this is the anomaly inflow scenario. And that also has very beautiful structures called the Storozumino descent equations. Okay, that tell you how this gauge anomaly and chiral anomaly are related from different dimensions. Okay, so I think I have shown the how this topological chart term appear, and also there's other situations in which the same story happens, okay, including collinear. I mean, it's so-called collinear corner electric field and magnetic field. That's not really applications, but I'm going to state it. And the chiral magnetic field. So for the original problem, like a Xiong problem, because you have the transition current, okay, you can compute the coordinator of this transition current, and you find this as a pole. That's called the Lucius pole a long time ago. Okay, and with this pole, you can start the anomalous order identity, and then you can find how to avoid the eta problem mass problem. And of course, you can also go to the Nanyang approach, following weighting, Veneziano, and division. That's also very well-known approaches. So I'm going to skip all this. So now I will talk about a little about the strong CV problem. Okay? So because this is a derivative coupling, so basically you have this shift symmetry. So the background value of alpha doesn't mean anything. You can just shift away. Right? So I have checked the gauge variation of this topological term is going to cancel out the gauge anomaly on the further. So the gauge variation is okay. So this is fine. But how about the CP? So my guess is the CP or the consolation for the CP variation also happens in the same way. Okay. And this solution is somehow follow the original proposition by TDD many years ago. It said if you consider the quantum numbers for both matter and the vacuum system, it's going to conserve. So here I just give my conclusion. So the original theta, the FFDO term, total term is replaced by a current coupling terms, and then check the gauge consolation and then the CP consolation. And that's it. Thanks.